Welcome back. So this is lecture 33 in this course, Bayesian Data Analysis for Behavioral Sciences. So the topic of this lecture is diagnostics for Markov chain Monte Carlo sampling. Okay, so MCMC diagnostics. So in the previous lecture, we implemented a Markov chain Monte Carlo sampler, and now we will see how do we inspect that whether our sampler has worked or not. How do we verify posterior recovery? How do we verify whether chains or the model has converged or not, or whether our sampling was okay or not, right? So we will do certain diagnostics to ensure that our algorithm has worked properly. Okay, so I will start right where I left in the previous lecture. So if you remember, in the previous lecture, we implemented a Markov chain Monte Carlo sampler, but we were getting a lot of NAs in our Markov chain, right? So our chain could sample up to 13 or so samples, and then it started producing NAs, right? You can see it here. Okay, and that actually happened because I will tell you why it happened. So it happened at I equals to 13. Okay, so the current state at I equals 13 was this. I'm showing you all this because you might also face this problem. Okay, so at I equals to 13, our new proposal that I generated was 0.07. Okay, likelihood of, so I calculated likelihood prior and all this, and let's see what it looks like. Likelihood of new proposal is this, prior of new proposal is this, likelihood of current proposal is this, prior of current proposal is this, right? So forward backward transition, and when you calculate Hastings ratio, it comes out to be 1. So in this case it will accept it. But what happened in that particular iteration was that somehow one of the density, so I guess it was likelihood current or something, so one of the density came out to be 0. Okay, so the either likelihood or prior density, not prior density, so one of the likelihood turned out to be 0. Okay, so if that happens, I think there is a mistake here actually. So this should be not proposal theta, it should be the current state in this case when we are calculating likelihood, the current state. Okay, and here when prior current, it should be current state. So I made this mistake in the previous iteration as well. But anyway, but this can always happen, because when you are calculating Hastings ratio like this, likelihood of proposal into prior proposal backward transition divided by this, if likelihood of proposal is 0, and that can happen sometimes when your data is, let's say, the proposal that you are evaluating, it's too extreme, so data is never going to suggest that this parameter can have some likelihood, then you might get a 0 likelihood for certain proposals, right? Also you might get a 0 likelihood for certain current state of the chains. Okay, in those situations, so if the likelihood of proposal is 0, then it's fine, then you will get Hastings ratio being equal to 0, so you will won't accept that proposal. But if likelihood of the current state is somehow 0, let's say, if it happens, then in that situation what happens is that your Hastings ratio will become infinite. Okay, so if your algorithm is not robust to that, so it can happen that Hastings ratio is infinite, and in that case you won't be able to basically accept or reject. If Hastings ratio is infinite, then basically it will start producing those NAs, right? And that sometimes that happens, right? So there are two ways to avoid this, because you can always get 0 value of the likelihood, especially for example if your likelihood is a normal likelihood and you have 500 data points, right? And when you can calculate joint likelihood, it will always come out to be 0, right, when you calculate it in R. So in that situation we use log likelihood, not the raw likelihood values, because raw likelihood values will come out to be 0 because there is computation limitation in R. But if you transform them on log scale, then you will be able to calculate large negative values, then it would be fine. Okay, so we operate on log scale, that I will show in the next lecture or so, right? But for now, in order to handle this, so let's say sometimes if by chance or by accident, if this h value of h Hastings ratio is infinite, then I will set a probability of acceptance to 0 or maybe let's say 1. Okay, otherwise I will go by this rule. The probability of acceptance is minimum of 1 in h, right? So basically you need to take care of those cases, that's the idea. But I guess after correcting this, maybe we won't fall into this state. Let's see, let me remove this part and let's see if it works. So I'm going to again run this same algorithm. Okay, so this time there are no errors and it has created a theta chain. So let us see how it looks like. I will draw a histogram of theta chain and this is how it looks like. This is looks like a very nice histogram and I think closer to your analytical posterior. Okay, we can compare it to the analytical posterior. So something using graph plots that we were plotting yesterday. For example, with plots like this. So analytical method, MCMC. So let's see. Now what happened? So post samples, it contains 4000 samples. This one contains how many? 4000 samples. This will, I guess, also contain, okay, 4000 plus 4000, 8000 samples. Looks fine. What is the problem? 8001 in one. Okay, so maybe this is due to this. Now it should be. I think it generated 4001 samples. Okay. So let me write it like this, not 4000, and samples. Okay, see. So this was analytical posterior, red one, and this blue one is sample recovered using Markov chain Monte Carlo. Okay, it looks good, not so bad, but it can be improved. Okay, one thing you can do to improve this is something like this. So let's say I increase the number of samples to 8000, and what I will do, I will accept on, I will burn first 4000 samples and accept last set of 4000 samples as actual samples from this chain. Okay, yes. So I will do it like this, 4001 to 8000. It looks like this. Slightly better, but it still can be improved, right? Would our posterior recovery become better if I reduce this step size to 0.2? Let's see. I generate 5,000 samples and I will burn in only first 1,000. Okay, so that is more reasonable to do. I will explain how, why. So this will become more clear when we generate multiple chains and when we visually inspect them. It's 11,000. Okay, 5,000. So my sample size this time is 0.25. So of course your MCMC algorithm is able to recover the posterior. You're getting basically your samples in the same range, okay, and the distribution also looks similar, but of course it can be better. Okay, so now one thing we want to see in this is to diagnose whether our algorithms are converging or not. Okay, so for diagnostics what I will suggest is this, that I will create an MCMC function so that I just change the argument of the function and it generates Markov chains multiple times. So let me create a function MCMC. The function take arguments such that number of samples that we can set to, let's say, 5,000. Okay. It also should take step size parameter. Then it should take what else do we need? So let us set it up 0.25, but you can change when you change the arguments, and number of rejected samples, which we initially set it up to 0, okay, and later on it will change. Okay, you don't need to actually create this here. You can later inside the function you can do this. Reject equals to 1 or 0. We start with 0. Okay. Now all this will be inside this function. You will each time you would initialize a theta chain, right, with n samples, initialize the Markov chain using your prior distribution, right, and then you will start collecting samples, right. So you'll do all these things. Step size will come from here, right, this thing, acceptance, right, you accept the sample or reject the sample, and once you are done with this, it should return. What do we want to return? So it should return these things: Markov chain, basically samples, which is theta chain. It should also return number of rejected samples. Okay, so these are the two things we want. Okay. So I've created a function for MCMC now. Okay, so now every time I want to do sampling, I just need to run this function. Okay. What I want to do is I want to generate multiple chains. Okay, so let me call them chain 1. So MCMC, I will call MCMC function for chain 1. How many samples I want? So let's say 10,000. And what should be my step size? So let's say my step size is 0.1. Okay. So I will generate first 4 chains with a step size of 0.1. So chain 1, 2, 3, 4. Okay. So I can also collect posterior samples from each chain. Chain 1 samples, chain 2 samples. Or rather than doing this, I can create a data frame actually. Data frame of posterior samples. So this is a data frame containing chain ID or chain number, which will be basically it would repeat 1 to 4, each one of them 10,000 times, or whatever an iter you decide here. Okay. So first I'm going to do this for 10,000 iterations and with a step size 1. Okay. So I will create a data frame where I store. See, this is taking time because now I'm generating 10,000 samples. It took some time. So repeat 1 to 4, each of them 10,000 times. And step size is repeat 0.1 or whatever step size determined. Here come number of iteration. So each step size, how many times? An iter into 4. And then samples. So for samples, you have chain 1 samples, chain 2 samples, chain 3 samples, chain 4 samples. You should also store sample ID so that we can visualize this in time, how chains are evolving. So sample ID should be repeat 1 to an iter, and this should be repeated 4 times for each chain. Okay, so this will give me the whole data frame containing all 4 chains. Okay, so now let us visualize each chain. How do they evolve over time? Okay, so this data frame, okay, ggplot df dot post aesthetic. On x-axis I want to give sample ID. Okay, on y-axis I want to give actual samples. Okay, group by, so group should be chain ID and color should also be chain. So these are the aesthetics I've defined. And now you can draw maybe geom line or geom point, doesn't matter, whatever you like. Okay, theme, let's say black and white, and you can facet wrap it if you would have, let's say, multiple step sizes, but that's not the case right now. Okay. So let's see how it looks like. See, this is how it looks like. Let me zoom it. So there were 4 chains. You can see here 1, 2, 3, 4. So 1 is dark blue, 2 is slightly less blue, 3 is slightly even less blue, 4 is quite light blue, right? And you cannot distinguish between these chains because they are on top of each other. They might have started at different places in the beginning. So for example, you see these long lines. So that probably happened because chain 4 started near 0.5 or so. Okay, but it moved upward. Okay, and then it started sampling from the correct posterior density. Okay, so it very quickly, let's say within 100 200 samples, it quickly converges to the posterior distribution. This is called convergence because within 200 300 samples, all the chains started sampling from the same place, and you would see that these chains would mix well. So you cannot distinguish between them, that which chain is sampling where. So they are mixing well. So that means this sampler is working really good. So there is no problem with the sampler. Okay. So now you can compare this against analytical distribution. So the number of samples I have actually now is 40,000. So I should compare accordingly. So let's say analytical has 40,000, MCMC has 40,000. I should give post samples MCMC. Post samples MCMC is all the samples in this DF post samples. This is quite good. So in fact, these plots look almost overlapping each other. If you want to, let's say, yeah, this is fine. We can see in critical region, let's say scale x continuous limits c 0.7 and 1. So this is doing fine. So our sample is doing quite good. Slight bit of problem it seems in this region, but that can happen, especially when the data size is small. So you have just 5 experiments, so it can happen in that situation. So for example, let's say sample size is 500. Now you might get much better accuracy. So it is taking time. Chain 1 took some time, chain 2 took some time because you are now generating 10,000 samples from the posterior. Chain 3 took some time, chain 4 took some time. You can visualize them here. So they look really well mixed. These are posterior samples. Just compare them. Yeah, so this looks slightly better. Much better than the previous one. So posterior recovery is also good, right? Now let us see what will change if you change the step size parameter. Okay, so what I'm going to do, I'm going to change the step size parameter to 0.01. Okay, so this is much smaller step size, and then I'm going to do sampling with this step size 0.01. Okay, and I'm going to store this in the same data frame. So I will R bind this to the existing DF post. Chains are moving faster, by the way. So let's see. Now in this case, you will need to facet wrap, because now there are basically two sets of posterior samples for each step size. So I will separate it by that. So let's see. So it does not seem there is a big difference when step size 0.1 and 0.01. So this is actually a good thing. That means your algorithm is quite robust to the step size. So it doesn't matter if you choose a step size somewhere as low as 0.01 and as high as, let's say, 0.1 or 0.2, right? It's working fine. Okay, so it's not a big problem. But what if it goes even smaller? Let's say 0.001. Now it's very small. So let's see what would happen now. Now you see the problems start occurring in sampling. See, this was for 0.1, this is for 0.01, so it was fine up to 0.01. But at 0.001, the chains start looking weird. Why? They are not mixing well. You can visualize this plot separately to see what is exactly happening. So let me just subset for step size equals to 0.001. See, the black one is chain 1. Okay, so black one started sampling somewhere here. Now it is moving in this direction. So although you are still trying to recover the posterior, you are still fluctuating in the posterior region, but the chains are not mixing well. So black chain is exploring in this region, so it took a lot of time to reach there at highest point, and then it will take a huge amount of time to reach backwards at the lowest point. You can visualize each chain separately. That black chain took a long time to reach here, so almost 1000 samples or 500 samples or so. Then it took another 1000 samples to reach the lowest point. That shouldn't happen. What should happen is that within a span of 100 to 100 samples, chains should be able to fluctuate from lowest to highest points. Okay, then your step size is good. But here it's a problem. Chains are not mixing well. They are moving slowly. They are getting stuck in a particular region for a long time, right? And if you would have number of samples up to 4000 or so, you will get a very bad posterior recovery. So let us see posterior recovery. This is for step size 0.001. So it seems fine. Actually, the posterior recovery seems fine because still all the chains are getting stuck, but overall they are fluctuating within that region. But it can go horribly wrong when this is not the case. Okay. So let us take one more extreme step size. Let's say 0.0001, even more small, right? And let us see what would happen. Now see, now they are completely off. So you can visualize each chain separately. So for example, this chain number 4 started at 0.7, I don't know, 0.68, and it took 10,000 samples to reach around 0.7. So it is trying to go towards higher posterior density region, but actually the actual posterior is somewhere around 0.8, 0.9. But it would take huge amount of time to reach there. So chains are getting slow, they are getting stuck. For example, this chain got stuck in this region, this chain got stuck here, this chain got stuck here, this chain got stuck here. They are not moving, right? Now you can see how posterior recovery looks like. See, the blue one, this is your posterior recovery. So it is not able to recover the posterior at all. So as you will increase this, it will start getting slightly better, but would still have some problems. So this is the situation with the step sizes of 0.0005. Okay, slightly better, but still quite bad. You can see posterior recovery. So it is matching the posterior in this region, but it is also sampling a lot of values from this region. Okay. So this is the effect of a step size. So there is one more effect of a step size that I discussed, that if a step size is too large, then your rejection rate would be quite large. So let us compare rejection rates when step size is 0.01. Okay. So in case of 0.01, chains are mixing well, right? And let's see the posterior recovery. Oh, what happened? Okay, I think there were too many chains with step size 0.01. We can see with 0.05. Chains are mixing well, everything seems fine. Okay, and posterior recovery is also good. Okay, let us see how things change in terms of rejection rate. So let us see the rejection rate of chain 1 here. So how many samples you rejected divided by total number of samples you collected. How many samples you're collecting? N iter. Okay, that's your rejection rate. So rejection rate here is 0.85. That's too high. That means out of 100 samples that you are proposing, you are rejecting 85 of them, right? So 85% is your rejection rate. That's quite high. Okay, and that will keep happening if you increase this step size parameter. Let's say you go to 0.1. So see what will happen at 0.1. Now the rejection rate is 0.91, and you could see that the chains are the sampling is getting slower because you are rejecting too many samples, right? Let's see what will happen with 0.5. When it is 0.5, see, now it is taking time. You can see this red dot coming here. So it is taking a lot of time. I guess you are going to reject around 95% or more samples. 97%. See? What if my step size is smaller? Let's say 0.001 or so. Now rejection rate is 6%. Okay. So in this case, basically your chains might get stuck and all those problems can happen, but your rejection rate is very low. Basically, you're accepting most of the samples. Okay, and this is not surprising, because when step size is too small, then whatever samples you are proposing, you are likely to accept them, because you are likely to move towards high posterior density region always, because you're getting stuck in lower posterior density region. So chain has tendency to move in higher posterior density region, right? So In Markov chain Monte Carlo, we want to achieve a rejection rate somewhere around 20% to 50%. So that's good. So let's say you achieve a rejection rate between 20 to 50%. So that's a reasonably good rejection rate. That means you won't get stuck. Your posterior recovery will be good, as well as efficiency will be also good. Let's see if we achieve this with a step size of 0.005. Yes, so this gives you a very good rejection rate of 26%, right? So that's really good. Okay, and now you see posterior recovery is also very good in this case. In fact, this is the best you have achieved so far. See, you almost cannot distinguish between the analytically derived posterior and the MCMC posterior. This is the case when your rejection rate was 26%. So basically, this is a kind of rejection rate where you are neither too slow, neither your step size is too large, nor your step size is too small. So in this particular problem, a step size of 0.05, 0.005 is actually really good. So you can always diagnose whether a step size is good enough, whether it is reasonably in good range by calculating rejection rate. So we want a rejection rate, let's say somewhere between 20 to 40 or 20 to 50%. Okay. All right, so I will stop here. This is it from my side on diagnosis of Markov chain Monte Carlo. In the next lecture, we will take some more examples. So we will implement MCMC samplers for a couple more examples, and we will try to recover the posterior, and we will do diagnostics for these Markov chains. All right, thank you.